then it will become C equal to A by 0, which is actually infinity, right? So which is actually not possible to deal with by the computer. So this divide by 0 is again an sort of interruption or error. Then unknown instructions. Suppose if there are any unknown instructions are coming on the way, right? So these are all some of the problems that may create an error or exception handling. And the errors and exceptions can happen at the kernel level services or task levels, right? So deadlock is an example for kernel level exception, right? So there are two processes, A and B. A needs some data from B to complete, and B needs some data from A to complete. So both the tasks A and B will be waiting indefinitely for the other task to respond, which may not be possible. This is actually called as a deadlock. And the OS kernel gives the information about the error in the form of a system call and a watchdog timer. Suppose if there is any problem, then there's a watchdog timer which will be available. And if the system fails to reset the timer periodically at some specified intervals, then the watchdog timer will try to give an alarm or will give the total process, right? So there are plenty of watchdog timer functions are available there. And the memory management, of course, the RTOS makes use of a block, right? So the memory will be divided into different blocks. And the RTOS kernel uses blocks of fixed size of dynamic memory, and the block is allocated for a task on the need basis. And the blocks are stored in a free buffer queue. Right? Something like if paging files in your Windows operating system. So a block of data will be read from the secondary memory storage, and that will be available in the primary memory while the task is getting executed. So all these things will be happening. And a few RTOS kernels implement virtual memory concept, right? So this virtual memory is also available. That is, if the system supports secondary memory storage, right? And in the block-based memory allocation, a block of fixed memory is always allocated for tasks on a need basis, and it is taken as a unit. Hence, there will not be any memory or fragmentation issues. And the block-based memory allocation achieves deterministic behavior with the trade of limited choice of memory chunk and suboptimal memory usage. Right. So whenever some task is getting executed, the data needed to execute that task, suppose if it is available in the hard disk, every time you cannot access the hard disk because it is going to take more time. So what we can do is we can take the related data from the hard disk and store it in the RAM so that the task execution will be much faster. So all these things also need to be handled with the real-time kernel. And interrupt handling, of course, we have already discussed about this. And there are two types of interrupts there. One is called synchronous and asynchronous. I think you have already studied about what is a synchronous and what is an asynchronous system. So a synchronous system works with the clock signal, right? So all the total blocks or total models, all the models will be working with a single clock. Asynchronous system, whenever the data changes, then there will be a corresponding reflection in all my blocks, right? So that is actually the difference between the synchronous and the asynchronous. And the synchronous interrupts occur in sync with the currently executing task, and usually the software interrupts fall in this category, because software interrupts will be writing the coding. So when that particular line gets executed during the next clock cycle, then that interrupt will be processed. Suppose if there is any divide by 0 or memory segmentation error, and all these things are there, so these errors will be reported during the next triggering point of my synchronous clock, right? That is actually possible. And for synchronous interrupts, the interrupt handler runs in the same context of the interrupting task. Of course, this can be done. On the other hand, if my interrupt is an asynchronous, right? Supposing if there is some external device, the interrupt is generated by an external device. There is another problem, and timer overflow is there, right? So the timer will be running with a different clock. Or there is a serial data. There is all of a sudden there is some data is available in my serial bus. So I need to process the data, right, from some external systems, you can say. So these can be considered as an asynchronous interrupts. And hence a context switch happens while handling the asynchronous system. So in that case, the OS should stop the currently executing task and should switch over to the next task, right, or the new interrupt. So that is actually called as a context switching. And the priority levels can be assigned to the interrupts, and each interrupt can be enabled or disabled individually. And most of the RTOS kernel implements nested interrupts. Already we discussed nested interrupts in the ARM Cortex M3, right? So when one interrupt is being serviced, when there is a high priority another interrupt comes in, then this interrupt will also be stopped or it will be preempted, right? And then the high priority interrupt will be serviced and it will come back to this. Then time management, of course, the accurate time management is essential for providing the precise space reference for all applications. And you will be having a higher resolution real-time clock. And the hardware timer is programmed to interrupt the processor at a fixed time, right? I think you should be having, there will be a real-time clock in each and every system. I think you should be knowing it. And the timer interrupt is referred as a timer tick, right? And is taken as the timing reference by the kernel. The timer tick interval may vary depending upon the hardware timer which we are going to use, right? So here there are two examples here. Actually, one is an microsecond timer ticks. For a 32-bit timer, so there are 2 power 32 combinations are possible, and each and every clock will be having a 1 microsecond, so 10 power minus 6 seconds. So what is the maximum delay that can be generated with this for one full counting of 2 power 32 bits, which will be equal to 2 power 32 into 10 power minus 6 seconds, which is equal to 1.19 hours. Suppose if the timer tick is 1 millisecond, right? So instead of 10 power minus 6 seconds, here we are replacing with the 10 power minus 3 seconds, and in that case I'll be having a time delay, maximum time delay of approximately 49.7 days, which is approximately 50 days, we can say. And the timer tick interrupt is handled by the timer interrupt handler of the kernel. And whenever that particular timer tick happens, interrupt happens, right? So we have to save the current context. What is the current task that is executed and what is the current status of that? So that should be actually saved. Then I have to increment the system timer register by 1 and generate timing error and reset the system time register if the timer tick count is greater than. Suppose if the task need to be completed within that particular time interval, and it could not be done, right, because of some errors. So in that case, whether we have to reset the total system or whether we have to generate a timing error. Right, and update the timers implemented in the kernel. Some timers will be incrementing and some timers will be decrementing, right? So count up as well as count down need to be done depending upon the timers. And suppose there are some periodic tasks, say for example every 10 seconds or every 10 minutes a task need to be executed. So only during that period the task will be active, the remaining time the task will be in the idle state. So we have to periodically activate those tasks and invoke the scheduler and schedule the task again based on the scheduling algorithm. So there may be plenty of scheduling algorithms will be there depending upon the tasks, and we have to invoke the scheduler so that the scheduling algorithm will be executed. And delete all the terminated tasks. Suppose if one task is completed, right, then that task control block and all the related data structure, everything need to be deleted. And load the context for the first task in the ready queue, right? So due to the rescheduling, the task, the ready task might be changed to a new one, which is preempted by the timer interrupt, right? So while scheduling as well as rescheduling, the data and the task should be available for the processor at the time. So all these things will be taken care of here. And now we will see what is the difference between the hard real time and the soft real time, right? So the real time operating system that strictly adhere to the timing constraint is called as a hard real time, right? So there should not be any missing of that the target time. So the deadlines should not be missed. That is what actually they mean to say. And missing any deadline may produce catastrophic results for hard real-time systems, including permanent data loss and irrecoverable damages to the systems or users. And say for example, it emphasizes the principle: a late answer is a wrong answer, right? It should be answered within that particular time. One example here is actually the airbag control systems or anti-lock braking systems in the vehicles. So supposing if I am going to use an embedded system for controlling airbag control, then immediately upon the accident my airbag should expand in order to protect the passenger. Suppose if there is any problem, if there is a small delay, right, then there may be issues with the safety of the passenger is actually lost. So in that case there should be a hard real-time systems are used here. And hard real-time system doesn't implement the virtual memory because these virtual memories may not be accessible at all the times, right, or may not be available, right? So this eliminates the delay in swapping in and out of the core corresponding to the task to and from the primary memory. And most of the hard real-time systems are automatic and it should not have a human in the loop. Most probably if the human is available in the loop, then what will happen? This hard real-time systems may not get executed. So it should be automatically executed because the human may not respond in time, right? That may be the problem. On the other hand, the soft real-time systems, you can miss 1 or 2 deadlines. That will not be a problem, right? So the missing deadlines for tasks are acceptable. And if the frequency of deadline missing is within the compliance limit, so there may be some quality of service definition. So every 1000 tasks, you can miss 1 or 2 tasks, something like that, right? So a soft real-time system emphasizes the principle of a late answer is an acceptable answer, but it could have been done faster, right? And in that case, actually, we can include a human. So even if there is any delay from the user, the human input, then that is quite applicable since it's a soft real-time process. One example is actually the automatic teller machine, right? So in that case, actually what happens, the user may take some more time, right, to give the inputs. So there may be some delay in the execution of the process. Again, that doesn't matter, right? So it may take some more time to give. Or we can have an audio video playback. Suppose if my decoding time, it takes more, right? So your video will not be continuously running. There may be some intermittent pauses will be there. Right, so but even then that won't create much problem, right? So these are all some examples for the soft real-time systems.